So we would like to give a brief outline of the proof of the prime number theorem according to Donald Newman. And for that, we use the wonderful, very, very short paper written by Don Zagier. So first of all, the prime number theorem is the statement that the limit as x tends to infinity of pi of x over x over log x is equal to 1. And of course, pi of x is the amount of primes that do not exceed x. So first of all, in an earlier video, we have established that this is equivalent. The statement is equivalent to the statement that the limit as x tends to infinity of theta of x over x is equal to 1, where, of course, theta of x is the Chebyshev function. Oops, this is a horrible sigma. Let's make sigma a little nicer. Okay. So the heart of Newman's proof, that one might argue uses some classical ideas, but they're pretty much optimized in a way that this is almost the most beautiful proof of the prime number theory that one can find. They're based on the following amazing observation that Newman did, that the prime number theorem follows. So the prime number theorem follows from the convergence of the improper integral from so the integral here is from 1 to infinity of theta of x minus x over x squared. So here pretty much what one does is to show that the upper limit as x tends to infinity of theta of x over x has to be less than or equal to 1. Because if it's strictly less than 1, then one can show that this integral has to diverge. And then one also shows that the limit as x tends to infinity of theta of x over x has to be greater than or equal to 1. Because if it goes greater than 1, then again, that integral would diverge. So eventually, the convergence of this integral shows that these two inequalities, that of course, they show that the limit of theta of x over x is equal to 1, hence the prime number theorem. So in other words, our attention now turns completely to the convergence of this integral. On the other hand, to establish the convergence of this integral, it turns out through an analytic theorem that is given, that has a very, very nice statement, that we need to make sure that a certain function is holomorphic on an open region, on a prescribed open region. So in particular, the convergence of this integral follows from two things. First, a general theorem on analytic functions, which is proven by using the contour integration. And secondly, the fact that if we define if f of phi of s is the sum over all prime numbers of log p over p to the s, then the function phi of s minus 1 over s minus 1 is holomorphic on an open set containing all complex numbers with a real part greater than or equal to 1. So if we can actually, so you can easily see from this definition that this function is defined and is analytic for real part as greater than 1. But if we can push this analyticity a little to the left by recognizing that this function has actually a pole at 1, then by doing this, we can actually prove that this integral converges and then have the prime number theory. So the question is, how do you analyze the behavior of this function? And to analyze the behavior of this function, one can show that this function is pretty much very closely related to the zeta function. So it turns out that phi of s is actually equal to a function which is comfortably analytic for on such an open region, which is this one. So this function can be shown to be analytic for real part of s greater than 1/2, minus the logarithmic derivative of the zeta function. That's pretty much what we call the logarithmic derivative. Actually, to be more precise, we should put a negative sign over here. And so for this, to establish this property that, in other words, phi of s minus 1 over s minus 1, so we can also subtract minus 1 over s minus 1, has the desired behavior. First one has to study the pole of this function at s minus 1. So one can show that indeed this function has a simple pole at s equals 1. And by subtracting 1 over s minus 1, we get that this pole is null. It's deleted in some sense. And secondly, one has to show that zeta of s doesn't have any zeros so zeta of s is different from 0 for s greater than or equal to 1. For s greater than 1, it follows from its Euler product representation. And for S equal to 1, we have a very nice little trick that is pretty much based on Euler's formula being e to the ix equal to cosine x plus I sine x. And it resembles the very classical argument that was initially used in order to also show that zeta of S is different from 0 when the prime number theorem was proven for the first time. So let's recap. So the main step is to understand that the convergence of this integral implies the prime number theorem. The second step is to have a general theorem on analytic functions that connects the behavior of this integral, or rather the convergence of this integral, with the analytic properties of this function right here, or rather of its difference with 1 over s minus 1. And finally, the desired analytic properties for this function are established by knowing that we have this relation to the zeta function, and one can show that the zeta function can be extended at least for real part s greater than 0, that it has the behavior, the expected behavior at 1, and finally that it's different from 0 for s with real part equal to 1. So again, these are the main ingredients. This is what needs to be proven, and by taking a look at Zagier's paper, it becomes quite evident that these are results that have pretty concise, not necessarily trivial proofs. The proofs are far from trivial, one might argue, but pretty concise proofs. And that gives us a very, very nice overview of how the prime number theorem can be proven. And that's all. Thanks for watching.